Welcome back. Today, we are diving deep into the cutting edge of real-time graphics. We're going to see how quantum computing can actually speed up one of the most common rendering techniques out there, screen space ambient occlusion, or what you probably know as SSAO.
All right, so here's the game plan. We're going to start by looking at some code, comparing the old classical way with the new quantum way. Then we'll get into the secret sauce, the algorithm that gives us this crazy advantage. After that, we'll see how you actually fit this into a modern game engine. And finally, we'll look at the benchmarks. Do the numbers hold up?
Okay, first things first. Let's get our hands dirty and look at some code. We're going to see how a graphic shader you might be familiar with transforms into something totally new, a quantum kernel.
So on the left, that's a standard GLSL shader. If you've ever done any graphics programming, this should look super familiar. It's a little program that runs on the GPU calculating pixel colors. But check out the right side. This is a CUDA-Q quantum kernel. And the first thing you should notice is it's just C++, but with one very important addition, that __QPU_attribute. That little tag is a signal to the compiler, NVQ++, telling it, hey, this function, this is meant for a quantum processor, or in our case, a very powerful GPU-accelerated simulator. You know, the key takeaway here is that a quantum kernel isn't some strange, abstract thing you need a PhD to understand. It's just a callable function. It feels a lot like writing a CUDA kernel for a GPU, and that familiar feeling makes it way more accessible for engineer developers who want to start playing around with this stuff. So now that we've seen what it is, let's get to the important part, why. Why go through all this trouble to run a quantum kernel for a task like SSAO? What's the real advantage? The magic comes from an incredible algorithm called Quantum Amplitude Estimation, or QAE. The best way to think about it is as the quantum version of Monte Carlo sampling, which is what classical SSAO uses, but this one has a serious superpower. And this right here is the math behind that superpower. To get a certain level of image quality, let's call it epsilon. Classical Monte Carlo needs a number of samples proportional to 1/epsilon². But QAE, it gets that same accuracy with samples proportional to just 1/epsilon. That's what we call a quadratic speedup. And believe me, in computer graphics, that is a huge, huge deal.
So how does it actually work? Well, it's kind of like a three-step dance. First, you have to take your classical data, in this case from the game's depth buffer, and encode it into a quantum state. Then you apply this special operator, which is a lot like the one in Grover's famous search algorithm, and what it does is it systematically boosts the probability of the answers you're actually looking for, the occluded pixels. And finally, you just measure the state to get your result.
And this just spells out the payoff perfectly. To get an image that looks as good as a classical render with 16 samples per pixel, the quantum approach needs the equivalent of just 4. That's a 4 times reduction in the amount of sampling work for the exact same visual quality. Okay, a 4 by sampling reduction is fantastic. It's amazing, but it's totally useless if we can't actually get it to work inside a game engine that needs to render a new frame every 16 milliseconds. So how do we pull that off? The key is a really clever design pattern called Async first dispatch. And the idea is actually pretty simple. You fire off the big, heavy quantum computation, and then you just move on. You don't sit around and wait for it to finish. And here's what that pipeline actually looks like. In one frame, let's call it frame N, the render system kicks off that quantum SSAO kernel asynchronously. Then it just keeps going. It runs other shaders, sets up its draw calls, does all its normal work. It isn't until the next frame, frame N+1, that it comes back and says, hey, are those quantum results ready yet? This completely avoids stalling the main render thread, which is absolutely critical. But you might be wondering, what if we didn't do that? What if we were just impatient and tried to get the results synchronously? Waiting for the simulator to finish its job right then and there. Well, the result is a disaster. You'd immediately blow right past your 16.67 millisecond frame budget. The game would have a massive, jarring stutter. For anything real-time, an async approach isn't just nice to have, it's the only way.
Now, time isn't our only problem. We also have to worry about memory. Remember, the same GPU running our Vulkan renderer is also running this quantum state simulation. And that simulation can be very hungry for VRAM. For instance, just simulating 28 qubits can take up 4 gigabytes of video memory, which has to fight for space with all your game's textures and buffers.
And this reality leads us to a crucial design rule for any of these hybrid engines, the zero quantum dependency principle. What that means is the engine must always have a classical fallback. If you run out of VRAM, or maybe the user's machine doesn't have CUDA-Q available, the engine has to be able to gracefully switch back to the standard classical SSAO. The quantum path has to be an enhancement, not a requirement. So, with all those real-world engineering hurdles in mind, let's finally look at the performance data. Is this quantum approach actually practical today? So in this table, we're comparing image quality using standard metrics, SSIM and PSNAR, where basically a higher number is better. And we're comparing against a super high-quality 64-sample render as our ground truth. Now look at this. The 4-sample quantum result isn't just as good as the 16-sample classical one, it's actually slightly better on both metrics. That is seriously impressive.
Now, there is a small cost, a bit of overhead, just to launch the quantum kernel, but this analysis shows something fascinating. As you increase the screen resolution, those massive savings we get from the 4x sample reduction start to completely overwhelm that initial dispatch cost. Once you get past 1080p, the quantum method actually becomes the faster option overall. So let's wrap this all up. What are the big takeaways? Well, first, quantum SSAO isn't science fiction. It's a really promising, totally feasible application for quantum acceleration in the near term. Second, that speed up from quantum amplitude estimation is real, and it's quadratic. And finally, thanks to powerful GPU simulators and smart asynchronous design, we can actually start exploring these kinds of low-qubit problems today. And all of this leaves us with one last big question. If a notoriously tough rendering problem like ambient occlusion can get a quadratic speedup with today's tech, what other big computational bottlenecks inside our game engines, in physics, in AI, in optimization are going to be next?